Boa noite, pessoal. Tudo bem com todos? Antes de começar a próxima palestra, eu vou dar alguns recados aqui para vocês. A lista de presença vai ser disponibilizada na descrição do vídeo e no chat ao longo da palestra. E como essa palestra vai ser ministrada em inglês, eu vou fazer a apresentação da Maria Esther em inglês também. Então, vamos lá. Maria Esther Brandan is a university professor in the Physics Institute of the National Autonomous University of Mexico, UNAM. Her present and past research include a experimental nuclear physics, radiation dosimetry, and medical physics. She was the creator and coordinator for 20 years of the medical physics program at UNAM, aimed at specializing physicists into medical applications. She has participated in more than 130 scientific publications. She is a member of the Mexican Academy of Sciences, fellow of the American Physical Society, and fellow member of the Academy of Sciences and for the Developing World. She has been president of the Nuclear Physics and the Medical Physics divisions of the Mexican Physics Society. Between 2010 and 2013, she was chair of the International Solid-State Dosimetry Organization. She has been awarded the Mexican Physics Society Medal for Development of Physics in Mexico and received the UNAM 2013 Premio Universidad Nacional in the area of research in exact sciences. She is current commissioner of the ICRU, member of the International Advisory Board of the Physics in Medicine and Biology, journal and deputy editor of the Biomedical Physics and Engineering Express journal. She is the head of the Experimental Physics Department at the UNAM Physics Institute. So let's start her lecture.
Thank you, Mariana. È un placer participar de este encuentro. Agradezco a doutora Alessandra Tomal por sugerir-me o nome e a João Carlos por coordenar minha participação. Eu só falo portunhol, então darei meu seminário em inglês, que é melhor que o meu português.
Ok, boa palestra.
Thank you much, Mariana. So I want to present the project that I have been leading at the National University of Mexico for over 15 years. And it is centered on a technique that's called contrast-enhanced digital mammography. Let me see how things are moving. Okay. Time is so short that it will be apenas un bo de pájaro. This is the roadmap. I will review general ideas about mammography, so we all know what we are talking about. Then I will center a little bit on what digital mammography has meant in terms of the special tools that gives to a physicist interested in the physics of mammographic images. And I will describe the beginnings of the project, the clinical experience, and the projects at this moment. So we'll start with general ideas that are still outside my project, so that's number 0. This is the curve that somehow motivates our research in mammography I have to learn, sorry, give me some patience. The x-axis is time, and these are the latest data, and the y-axis is the rate of mortality from breast cancer for women about between 30 and 85 years old. And what I want to point out is the trend with time. Some 30 years ago, United Kingdom, USA, Germany, Brazil, Mexico were increasing the mortality year after year. But in year 90, something happened that was good for the 3 industrial countries in the plot, and that apparently did not affect what was happening in our 2 countries. And the tendency changed. And instead of continue increasing and increasing, it started decreasing. And thanks to what happened in the 90s, the United Kingdom, for instance, decreased by 40% the mortality from breast cancer. These are numbers normalized by the population. Our countries did not show any change, and our trends, our mortality grows year after year. Which is the explanation for the change in the 90s? The evidence suggests that the reduction that started in industrial countries in the 90s can be consequence of early detection of breast cancer. Thanks to the implementation and improved therapies. The goal of a breast cancer screening program, is to detect a cancer before there are symptoms, before it can be touched. The breast cancer, how is this done, this early detection? It is mostly done using mammographies, because the mammography technique still permits to detect a cancer when it's small and when it's confined to the mammary gland. If it's detected that early, it will have a better probability of being cured. So what is a mammography? A mammography is a study, a radiological study, is an X-ray picture of the mammary gland. It is the only method that has been validated for the early detection of breast cancer. Its sensitivity is about 80%, is less in certain groups, and its specificity is about 90%, also depending on the conditions. I consider mammography as the most demanding radiological study in terms of image quality. To obtain a good image of the mammary gland is technically very difficult. These are 4 views, 2 for each breast, of a standard screening program, of a standard screening study. So this is the image that every woman older than 40 or 45 years old should be getting every year or every 2 years, depending on the recommendations in her country. I'm sorry, in Portuguese, exquisito means something very different. What I mean is a technically perfect image, a very good image, because the contrast you are seeing is between soft tissues. The glands, the mammary glands, have no bones in it. It's all is soft tissue, and in an image, in a mammographic image, you must be able to distinguish fat from fibroglandular tissue. And these images are images of good quality. And what I had put in the oh, you don't, maybe you see my cursor. In the circles are the suspicious lesion. You can appreciate that you need to be a specialist in radiology to distinguish, to identify that this part is a suspicious region. In fact, this is a highly suspicious lesion that is seen in the 2 views of the study. The study is acquired using a mammographic unit that is an X-ray tube. Here at the top, X-rays travel down. Here there is a compression plate, and here is the breast of the patient. This is the physics of mammography. X-rays attenuate according to the exponential law for a monoenergetic beam. If it's polyenergetic, you just add up all these attenuations coefficients over the spectrum. And what these curves show is a linear attenuation coefficient for tissue that tissue. B means fibroglandular tissue, tecido o fibroglandular, and C is a cancer, a carcinoma infiltrante. And you will see that there is almost no difference between the attenuation properties of cancer and the cancerous tissue and the attenuation properties of fibroglandular tissue. Adipose tissue is less attenuating, and that's why we see it as gray or black in the image, and all the white is due to fibroglandular and the lesion or a cancer if it is present. So it's against this similarity in the curves that all the technological advances are confronted. So let's go now to a mammography, to a digital mammography. Digital images arrived in mammography with the change of century in year 2000. Probably many of you were not born at that time or were babies at that time. But we, the older people, faced the revolution when digital arrived. But what is so special about digital? When I learned how radiologists look at mammographies, came to my mind this that is in Spanish, it says, ¿Dónde está Wally? I don't know how you say it in Portuguese. But this is a Wally, where is Wally picture? And in fact, picture one, image 1 and image 2 are not the same. They are different. So I ask you what to do. ¿Dónde está Wally? Thank you. Gracias. My question is not ¿Dónde está Wally? Because that's an easy question to answer. It's easy to find Wally in a picture of this because Wally always dresses the same. He's always with the same t-shirt, with the stripes, and with the same hat in his head, always the same color, always everything. So it's just a matter of looking after him and finding. But the radiologist has a harder work, a harder task than finding Wally, because the radiologist has to look for a lesion that can have several shapes, that can have several contrasts, that one could simulate, say, several colors. And it's just all the training of the radiologist that takes him or her to this. So I ask you, which is the difference between? So there are two ways of doing. One is to start looking at the images, for instance, from top, left, right, looking at one and looking at two, trying to identify the difference. But I tell you, as a physicist, if these are digital images, we can do it very easily. We can find with mathematics the difference between two numbers, because a digital image is a matrix of numbers, just using the arithmetical operation that's called subtraction. Subtraction of, in Spanish we say sustracción o diferencia. There are two names for is to find a difference. So I said, this is trivial. Why don't you subtract I2 minus I1? So here is I2, image I2, and here is image I1. So go pixel by pixel, subtracting the two numbers, and you will get 0 whenever everything is alike, and you will only have different from 0 when there is a difference. So we do the subtraction, and the result of the subtraction is this. there is here a yellow point that it is in image 2 and it was not in image 1. I show you again the two images and what it is. Here in image 2, there is a ball, a yellow ball, una pelota amarella, yeah? And that is the difference. Well, I have shown you the power of subtraction. Whenever you have numbers and you want to find difference. And that will be very important for our project. Our project is based on subtraction of images. Digital mammography in general offer many advantages over the old-time mammography that was done on radiographic plates. I don't have time to go through them. Maybe some of you already took a course on digital imaging and knows all this. That is very basic. There is a wide dynamic range. That is the quantity of gray levels for a mammography is to optimize each stage of the mammography independently. You can do image processing, you can do image post-processing, and you can, using all these, there are tools to help diagnosis, and you can even have three-dimensional mammographies. All these thanks to the digital character of the image. But not only that, some new techniques have arisen thanks to digital mammography, and they are called dual energy mammography, contrast enhanced mammography that uses a contrast medium and energy subtraction, and tomosynthesis that is a 3D modality of mammography. In this talk, because that's what my group does, I will center in the first two. So I'll be talking about dual energy mammography and contrast enhanced digital mammography. So that's how we define the project some 15 years ago, maybe more, and how we started. We started as any project in a very simple, maybe artisanal way. Dual energy subtraction looks extremely attractive for a physicist. What is the idea? The idea is that we acquire two images of the same object, but with different spectra, with different X-rays, with X-rays produced by the tube under different radiological conditions. And we subtract one from the other, in order to eliminate one of the objects, one of the media, let's say bone or tissue or glandular tissue or adipose tissue or microcalcifications in the image. How can you do that? You can do that because of the physics of the mammographic image in general, of any image, because you do this very regular today with CT, with computed tomography images. These are the mass attenuation coefficients for different elements. We have soft tissue, bone, calcium, iodine, gold here. And these are, here we see the dominance of the photoelectric effect. I mean, this is a low energy region. And you subtract one from the other, and one of them you multiply by a weighting factor that determines which of the tissues will disappear after the subtraction. And this is an example of a commercial announcement by Philips, where you have a chest X-ray acquired with a low energy beam, a chest X-ray with a high energy beam, and they look very different one from the other. One is not a multiple, a factor of the other. There are qualitative differences due to this nonlinear dependence of the attenuation coefficients. And here is the result. Depending on the alpha you chose, you can eliminate the bones and be left only with soft tissue, or eliminate the tissue. These were examples, and we got inspired by that 15 years ago. And we started with a simple problem. We said, oh, we have microcalcifications in the image. And the radiologist told us the problem is that sometimes these microcalcifications are just on top of the fibroglandular tissue, and I cannot see them. I said, well, we will subtract 2 images, trying to eliminate the fibroglandular tissue, so you will only see the microcalcification. So we built a phantom, a plastic phantom, and on this wax strip, we put a lot of human microcalcifications. We took a low energy image, a high energy image, and we subtracted, trying to send the wax to 0. That was our goal. We chose alpha so that the wax go to 0. Here you see it, and only the microcalc survive. So apparently everything went well, but no, it didn't go well when we put numbers. This is the contrast to noise ratio. So this contrast divided by noise has to be larger than a value, I don't know, that could be close to 5 according to a criterion. And we see that these are 300 micrometers diameter microcalcifications. These are the calculations done by Veronica Ramirez. She was my student in this project. So she predicted that. She measured those points with her phantom, but the results show that as the breast or the phantom, your contrast to noise decreased and approached the Rose limit. And for most of the breast, we will not be able of seeing the microcalcifications because they will be immersed in noise. It was the noise in the background that will prevent the visualization of the calcification. So this was a beautiful thesis. That was our first in the subject, but we learned that application, it was not possible. So let's go to the second. We had here a second option that was not to trust in the breast the materials that were naturally present, but to use contrast medium. To inject contrast medium in the circulatory system of the patient so that the iodine, in general, this is clinical contrast medium based on iodine, will tell us something about the functioning of the breast. So our program, our CEDM project started then on those years after our failure with dual energy. And what was offered to us? It was the possibility of use a contrast medium to visualize a lesion thanks to angiogenesis. That is a biological process in our bodies, in fact, in the bodies of mammals in particular. So angiogenesis is the formation of blood vessels from existing ones. And here there is a cartoon, no? Here you have a tumor, and the tumor sends some molecules that tell the vessel, I'm hungry, I need nutrients, please send me nutrients. And the blood vessel obeys the order, and new blood vessels grow to feed the tumor. Of course, that's not good if we want to stop the growth of a tumor, but it's great for the tumor. So these new vessels allows the tumor expansion. Every tumor larger than 1 or 2 millimeters requires new vessels. But, and that's the detail, how will this help us to see it? The new vessels are immature. They have pores, boracos, I think you say, no? Liquids leak out, no? O líquido derrama, no? So, if the liquid will come out of the vessel and this liquid contains iodine, and iodine attenuates X-rays very well, we will see a spot, a white spot in the image, indicating that the liquid that was, that there were leaky vessels that allowed this to happen. So we started our program. Our first two theses were by Vianney and Ivan. Both are doctors right now. Oh, I'm sorry, I'm going much too fast. And what they did, I decided that since we were opening this new field, we needed a form things in a quantitative way and to optimize and to predict. So they created formalism to subtract images using dual energy, we thought, in a modality trying to improve visibility after the subtraction, and also in temporal modalities. They optimized the acquisition. They did calculations that were validated in phantoms, and we calculated. So we went with a quantitative approach some 13 years ago. Now, something very interesting is that this technique transforms mammographies into functional images. They are not only anatomical. So what's the basis of the formalism? The basis, if it's dual energy, in this case, it would be dual energy, but not with tiny microcalcifications, but with large spots of iodine. So maybe it will work better. So we have two images of the same object acquired with different spectra. One of them is weighted and they are subtracted. So here is the relation that describes, and which is the price after the subtraction. One of the two media, one of the media present in the image gets eliminated and the other survives. One adjusts the alpha so that happens. But the other way was to do a temporal subtraction. So if we will inject this contrast medium into the patient's body, we will be able, subtracting the two images, as with Wally, to know what was in the normal breast and what was added when the contrast medium passed and leaked out. So in that case, we use only one spectrum, but two different times. And this was continue being the work of Vianney and Ivan. So this is the type of results I don't expect you can understand in depth because we are going much too fast. But here is what we want to attain. We want to increase the contrast so that our eyes or our machine, our calculator or our computer will see the difference between the two objects. So this is the contrast as a function of the quantity of iodine that is present in the lesion in milligrams of iodines per square centimeter. What we have had very clear from the beginning of our project is that this was going to be a quantitative evaluation of techniques. So everything worked fine, and Ivan and Vianney worked with phantoms, with plastic phantoms. But as soon as we had access to clinical images, where the background was not homogeneous, we started having problems. And another student, Juan Pablo Cruz Bastida, who is also a doctor at the moment, a postdoc in the University of Chicago, he devised an image processing, subtracting not an alpha, a number, but a matrix. As I said, I don't have time for details. So this finishes somehow our beginnings, working with phantoms and very simple system, and we get into a clinical experience. And fortunately, we had a collaboration with the National Institute of Cancerology close by in Mexico City. Also, for this work in particular, we work with another hospital and also with some collaborators outside Mexico City in the state of Oaxaca. So this was the title of our clinical project, our first clinical project, extremely complex to perform as everything you do for the first time, particularly with patients. And what was the goal? Was to do a clinical study of digital mammography with contrast medium, and at the same time to correlate with samples taken in biopsies of the patient, so that we could correlate what we saw in the image with the biomedical, with the medical real information in terms of number of blood vessels, microvessel density. So here we see and we had two branches, the dual energy and the temporal branch, trying to evaluate if one had advantages. It turned out that no, they hadn't. So at the moment we choose one or the other, but we don't do both. So here we have an image, a low energy image, where we have identified adipose tissue, delisio, glandular, the same taken high energy. We put these markers so that whenever we subtract the images, since there is motion, we can register one motion. This is a high energy, and this is the high energy where the contrast medium is. And this reminds us as our Ondestawali situation, which is the difference between this with contrast, with iodine, and this one. Our eye doesn't see it easily, so let's use mathematics to subtract. And it's in the subtraction where everything will disappear except what was added by the contrast medium. So the objectives were to correlate the parameters in the image with an histologic analysis of the microvessel density. This is the protocol. I have now 17 minutes left, or maybe less, probably, no, 12 minutes left. So I'll go fast. You have to define a very careful protocol because you are dealing with patients, but of course, this had to be approved by the Ethics and Research Committee at the National Institute of Cancer, and that included to take images before injecting the contrast medium, and then to take 4 images afterwards, and we will be subtracting the contrast images from the non-contrast images. This is published if someone wants to read all the details. And as I said, we are quantitative, and the parameter was very simple. It was contrast, defined in the symbols in the simple possible way, is the concentration of iodine in the lesion minus glandular tissue. The radiologist indicated where the tissue was, and the images were calibrated into thickness of iodine, so they had a physical meaning. And one of the results, this comes from the biopsy. This is an image. We saw that our patients with cancer had more vessels than the patients without a cancer. And this is one of the images. This is a 68 years old patient. We call her patient one. And we have this woman had an invasive ductal carcinoma with necrosis, and that's a mammography. This is a normal mammography, but this is a result of the subtraction. And it's very interesting because, as you realize, most of the structure of the breast disappear after you subtract, because it was before and it is later. What is new is the arrival of the iodine. And here you have minute 1, minute 2, minute 3, minute 5, and you see how the iodine increases. The white, the color white is higher here than here, for instance. So it gives us a dynamical information, and the iodine is not entering the center of the tumor. And later we knew that this case had necrosis. So there were no vessels to enter at the center of the tumor. That was the positive case. This was a cancer. And this was a negative case for us because we did the same with this patient. This was patient number 7. And here we see clearly the accumulation of iodine, but this patient did not have a case of cellular fibroadenoma. So there we learned that angiogenesis is also present in cases of inflammation, and that taught us to be very careful and not to use this technique as a yes or no just from looking at it. We also studied the time evolution of the iodine. I will show you just very rapidly how the data look like and all the work that was involved. And the conclusion was that the technique, in fact, increased the lesion visibility and showed additional features, such as the borders or the rims, and this was a very interesting technique. The radiologists immediately adopted it for the service, and today Instituto Nacional de Cancerología offers contrast-enhanced digital mammography thanks to this first study. The technique is already commercial. We are not part of the business. The technique is commercial, but we are not part of the business, but we know all the secrets of the business because we developed our own way to do it in-house. So we jumped to today, at the present. I was just want to mention, in the 7 minutes left, 2 theses currently in progress. This is a PhD thesis by Lisbeth Ayala, who was my master student some years ago. It's a thesis on biomedical sciences, not in physics. And the goal is, I will see the title. She's looking for parameters, searching for quantitative images, but in a micro system, because she's working with an animal model. She's working with rats that have a glioma induced. In fact, as I don't know how to say injertado, but it's a xenograft. And the idea is to systematically quantify the parameters with technique, the only one energy temporal, dual energy, or a dynamical technique, and to evaluate the correlation with biomarkers of angiogenesis, but in an animal model. This is the arrangement. Here is the animal, and here is the X-ray tube. This is a commercial micro CT equipment. The tube goes around and the detector goes around. And this is the type of images after reconstruction. No, this one is after reconstruction. And here you can see the contrast medium arrived to the heart. And you can see it starting moving around the big vessels in the body. This is, I will not have time. These are a sample of data for single energy, for dual energy, and for dynamical contrast enhancement. I will jump to the results. She's very close to graduation. She's publishing her paper. And what she has found is that there are certain biomarkers, for instance, relative blood volume, that she obtains from any of the three techniques, which significantly permit to distinguish central from the peripheral tumors. The rectangles here and here is only the tumor. And there is always an image without contrast medium, with contrast medium, and the subtraction. So this is the subtracted image where everything you see is iodine quantified. Here, she does it by dual energy, and she obtains the same. And here is for dynamical enhancement. So this is one of the projects. So we have moved the big questions that we had with the breast, with the clinical, down to the preclinical studies. This is the second thesis. This is a these are the results by Liz. We'll move to the second thesis. This is Gustavo Pacheco, a student of the master program, and he's using, we're for the first time trying to apply our dual energy formalism in order, you remember, dual energy permits to eliminate one type of tissue from the other. If we want to eliminate fat, grasa, no, we are left only with glandular. And if we change the value of alpha, we will eliminate the fibroglandular and we will be left only with fat. So we will have a separation of components in the breast of the patients using dual energy, and that can help us to calculate which is the volume, which is the relative volume in the breast occupied by glandular tissue with respect to the total. And why is this important? Because that's an indicator of risk. Into a different problem is the evaluation of risk, starting with a mammography. Since very long, since last century, it is known that the breast glandular density, that is how much glandular tissue do you have in your breast, correlates with the risk of developing breast cancer. And here we have 4 images taken from this review that was published not too long ago, where you can see 4 types of breast. This has very low fibroglandular tissue, not much white in the image, is mostly fat, adipose. This has more than this has more than this, and this has much more than this. So the glandular density increases from A to D, and in general, doctors look at the mammography and in a very subjective way, they try to imagine which fraction of the area is occupied by fibroglandular tissue. They estimate a risk factor for the patient. In certain places, in certain states of the United States today, is enforced, obligatorio, to give that value, to estimate a value of risk, starting from an evaluation of breast density. But it has to be quantified. This is the time for digital. So you can put numbers. You should put numbers. And these are Gustavo's results, preliminary results of his thesis. Here he applies our dual energy formalism, distinguish one from the other. So he sends fibroglandular to 0, and he only gets adipose tissue. Then he does the opposite. He sends adipose to 0 and he only gets glandular. These are thicknesses because the method is quantified through a normalization. Then he adds this to this and he gets a total thickness. Since the breast is compressed, one will expect that the thickness is the same everywhere except at the borders, but the method has a technique to take borders into account. And then he does the ratio, glandular over total, and this is what he get. And here you can see we always have a scale that gives us values in physical units. And in this case, it's a glandular ratio. So when we see white is a lot, black is little, where we see white is where we see a high fraction of glandular tissue, but already in thickness. So we can do 3-dimensional measurement out of a 2-dimensional image. Very neat. So the results so far, Gustavo is very ready to finish writing his thesis, his master's thesis, and get the degree. We have developed a method based on subtraction of dual energy to calculate glandular tissue volume for 14 patients. And we have a new student who is starting to take over this project to move it forward. So we have gone through our project in these last years in a very rapid vol. No, we have flown, or I have to recognize, I'm sure I'm forgetting many, but here are some of the names, my great collaborators, Yolanda Villaseñor, she's a radiologist, and Luis Benítez Briviesca, he was a pathologist. And here are my master students, 4 of them already doctors, and 1 of them in my group, back in my group after his doctorate. And here are the present students. These are the 4 working at the moment. These are external collaborators, external to this project. And that's some of them. And well, I want to thank them, but also I want to thank you for your interest. Well, thank you, the organizers. It's been really a pleasure.
Obrigada. Thank you, Marister. Was a
Mariana,
pleasure. Was a pleasure to watch your lecture. Obrigada. We're going to start now about some questions that you left in the chat. So I'll translate for English so that everybody will understand. According to the graphic in the beginning, what's the explanation for the raising of breast cancer in Brazil and Mexico and decreasing in UK and the USA?
Oh, thank you, Perseu.
As a question from Perseu de Paula.
From Perseu de Paula. The analysis of this graph is a conference by itself. So it takes me 45 minutes to discuss everything what we have analyzed from the perspective of Mexico. What is the most common, as I said, the common explanation, and I will say that is accepted by almost everyone, is that in the year 90s, the screening programs, I don't know how you say screening in Portuguese. In Spanish, we will say tamizaje or cribado, which is a program that tests open population without symptoms for a given disease that has some probability of occurring. in these years, the first screening programs, organized, centralized screening programs started, and they were implemented rigorously by industrial countries. So a screening program consists of some technique for early detection of cancer. In this case, for breast cancer, is the realization of a mammography in women older than 40 or 45 years old every 1 or 2 years, with following a very rigorous protocol. The coverage, the number of women responding to have a mammography has to be above 70% of the population if you want to see results as this. If it's below 70%, your results will not be this evident. And it includes a series of technical requirements, no? To invite everyone to have sufficient services to offer the mammography. They have to be well equipped. The equipment has to be in good quality. So there must be quality control or quality assurance programs behind. A quality assurance includes to have a sufficient number of specialists who will act in each of the stages, specialists for the acquisition of the image, specialists for the interpretation of the image, and if the result is negative, let's say a probable cancer, there must be a system that confirms that that's a diagnostic and that offers the right treatment. So this is very complex, very expensive, and requires lots of organization. These 3 countries that are here happen to implement such a screening program in the 90s, and the results started to be observable very rapidly. I cannot talk about Brazil. I just found when I was preparing this talk that the curve for Brazil looked very much like the curve for Mexico. For Mexico, there has been an organized, established program. There has been investment in buying equipment, but for instance, there is no, even if the law requires a quality assurance program at each service, this is not complied with. And services, even if they do not have quality assurance and quality tests, still perform the mammographies, and the quality of the images, and that's something that my group has analyzed very carefully all over 20 years. Also, the quality of the images is not acceptable. So we think that no equivalent program to this was implemented or has ever been implemented in Mexico. And as physicists, we have evaluated only one of the, I don't know how you say, of the links in a chain. A chain, una cadena, is made out of links. And this has many links, and all of the links must work. And we have analyzed the image quality link, and we have found very poor results. So our interpretation is that we don't have a well-structured and efficient screening program. And that's why we don't see that the tendency reverses.
Okay.
I don't know.
Yeah, I think it's answered. There's the next question here is if food or what you eat interferes in the causes of breast cancer, or would there be other causes that apply? From Leonardo Ribeiro de
That's an
Souza.
excellent question. Also, Leonardo. Also, there are multiple factors associated to the probability of expressing breast cancer. The most important is to be a woman, since 90% of breast cancers show up in women, and the other 10% in men. So men also express breast cancer. But so one would say the higher risk factor is to be a woman. The second risk factor is the age, since the probability of expressing it increases almost exponentially with age. And that's why the screening programs address a population starting at 40 or 45 years old. And those are inevitable. I mean, one is born a woman, and that's it. And one grows old, and that's it. No? So what else has a weight? The exposure to estrogens, estrógenos, and that has been observed, for instance, that the age, and I don't know how to say anything of this in English much well, and even less in Portuguese, but for instance, for a woman menstruation, and the arrival of menopause define how many years a woman is exposed to high levels of estrogen. That could have an impact too. That's why women, there is a larger probability, a larger incidence of breast cancer in women who have had no children or who have not breastfed their children, because they have been exposed to more. Yes, you continue with the risk factors, and yes, alimentation becomes important, but it's not that clear. I would say that the advice is live a healthy life. No? Eat well, do exercise, as for many other things today. There are also genetic factors, and one hears about BRC1 and BRC2, but it's a small fraction of the population that carries those risk factors. Yeah?
Mm-hmm.
Yeah, I think I answered which other
Yeah.
factors will be. Yes.
Mm-hmm. Now, from Marina Cabral, would it be possible to develop a different approach to mammography machines? In the region I live in Brazil, many women are concerned and even afraid to get their exams done.
Well, yes, certainly. There, there, there are many techniques, but still in the stage of research. So
Mm-hmm.
there are techniques, for instance, magnetic resonance expensive. So you cannot use it's expensive because it's a long examination. So the machine could only receive a few patients compared to how efficient it is with a mammography. But certainly there is research and there is interest trying to find an alternative or a complement.
Mm-hmm.
About the concern for having an exam done, this is an education problem in part. In part, it's educational, and we see that in Mexico. Two, there are mitos, no?
Mm-hmm.
One should know, and as a physicist, we should know that the dose, the radiation dose delivered by a mammography is a low dose, even, it's not, I mean, it's a low dose in terms of it is equivalent to, in this moment, my numbers fail, but certainly is equivalent to less than 1 year of natural radiation. No, so that is comparable to doses that we will receive naturally anyway. So in terms of dose, if the mammography is well done, is well taken, so it doesn't have to be repeated immediately because something was forgotten, no, that is an educational problem of the service. uh, to have one mammography study done every year or every 2 years has more benefits than risks, by far, 10, 100 times more. Now there are other it's true, it's bothersome. I mean, no one likes to have her breast compressed during a minute or half a minute. But there are many other things, I think, in life where we learn that is worthwhile a minute of being uncomfortable because there is something much more important to be gained. So I think mammography should be done with equipment that is working with good quality. Even the older equipment, I mean the non-digital. I mean that's another question, no? Would you only digital mammographies provide good images? No, no. To be digital, it doesn't mean that the image will be good. That depends on what is the service and the maintenance for the equipment. And there are still some old equipments based on radiographic film that, if subjected to a rigorous quality assurance program, can provide excellent images. So it's complex, but I think what you say, that many women in Brazil are afraid to get an exam, I think is an issue of education. And also, the screening programs that worked in these countries always include a strong educational effort. If someone wants to start, you don't have to reinvent anything. There are books published by the World Health Organization, among many others, with instructions on how to do it. The problem is that it's very expensive. It's very expensive because you will be finding a few cases in your open population through a program that requires to educate specialists and to have physicists, among others, in charge of assuring the quality. But that's a field of work for medical physicists that, in countries where mortality is a problem, is a health problem, I would say that we are countries where this is a health problem because we are in the 20th century, in the 21st century, and our mortality increases and increases while the rest of the world is already controlling the situation. It will be expensive. That I think each country must find the ways to do it in the most efficient way, and medical physicists are essential because of the quality. If the image is not of quality, the radiologist will not find, it will not be able to do an early detection. Alessandra. Hola,
Yes,
Alessandra.
she's here watching you.
She's
Which is
here.
Yeah, which is considered the best approach in terms of additional information extracted from images or dose. Dual energy or temporal contrast enhanced digital mammography.
This is a question for Sandra. It depends. It depends on the situation. I love the temporal information, but for instance, the companies have chosen the dual energy approach because the dual energy approach, and there are lots of clinical studies done by now. The dual energy approach is more comfortable because you apply the contrast medium and the patient can be sitting very nicely in a chair, and after the application, the injection, she's moved, and then the two images are taken at the same time once the contrast medium has entered her breast and is already circulating. And they have gone through that way, I think, because of the comfort of the patient and because of being two images taken at the same time. There are very few motion artifacts. In the temporal, you need an image before and then the images after, but all of the same object. So the patient has to be compressed already when you inject the material. And that poses a problem. That was one of our problems in our clinical study. But I like the information of the dynamic curve where you see the iodine getting in and then getting out. I will say that one of them has been much more explored than the other, dual energy, because the equipment exists. We are capable of doing the two of them, but it's very difficult to justify more clinical studies than the ones we've done. That's why we moved to preclinical with our present students. I would say each one has advantages. There are publications for both, for one much more than the other, as I said, and it depends on what you want to learn, probably, or what are your possibilities of doing. But commercial only for dual energy. And
Okay.
un gusto verte nuevamente, Alessandra. Verte,
Sí.
leerte.
I think our time is already exceeded. So this was the last question. And we would like to thank our sponsors, such as Varian, Electa, ABFM. And well, that's it for today. If you want to share your email with the people
Absolutely.
watching you,
Yeah.
Marister, so they can ask other
Yeah.
questions that were in the chat. Yeah.
Of
So
course,
then,
I
yeah,
will.
we can.
I will answer all emails, not immediately, probably,
Mhm.
but certainly I will answer. Yeah.
Yeah.
Well,
So
thank you much to you. It was
thank you
great
very much for
with
your
you.
lecture, for your time. It was a pleasure to have you here.
Thank you, Mariana. Thank you, everyone. Bye bye.
Goodbye.
Adios.